Okay, so it's time to have a look at structural isomers. So these are molecules that have the same molecular formula but a different arrangement of atoms. And we can split them up into three different types: chain isomerism, position isomerism, and functional group isomerism. Let's take each of these in turn. So chain isomerism, let's put an arrow down like so. So what we're looking at, for example, is the difference between, say, butane, so carbon, 4 carbon atoms, and some hydrogens. So we've got 4 carbon atoms and 10 hydrogen atoms. And its chain isomer pairing, as it were, would be 2 methyl propane. So where I've got 3 carbons and a side group. And as you can see quite clearly, we have still got, if I can squeeze them in, all the little hydrogens, exactly the same molecular formula. They are both C4H10. Now, if I were to draw them out using skeletal formulae, so butane and 2-methylpropane, yeah, I'm going to put the group up in this case. And let's have a look at their boiling point. So the boiling point of butane is 273 Kelvin, and for 2-methylpropane it's 261 Kelvin. So we can see that isomerism has an effect on the physical properties of these isomers. In this case, they're going to have exactly the same chemical properties, which for alkanes is they're great for burning, not much use for anything else. But they definitely have different physical properties. How can we explain that? Well, boiling point is all about intermolecular bonds. Now, because they are both alkanes and they've both got the same molecular mass, their intermolecular bonding is going to be of the same type. They're both only capable of forming instantaneous dipole-induced dipole intermolecular forces or London forces, whichever way you like to say that. However, it's quite clear that butane has got stronger intermolecular bonds because it has a higher boiling point. Quite often in an exam question, the question itself gives you the answer. Why might that be? Well, the reason is because molecules of butane can pack more closely together than molecules of 2-methylpropane, which means that the intermolecular bonding in butane is stronger. It's more effective. We need to remember that instantaneous induced dipole forces, London forces, are very, very weak intermolecular bonds. They're very, very short range. So the closer one molecule can get to its neighbour, the more likely an induced dipole is going to occur in the neighbouring molecule. So that's chain isomerism. The next one I want to have a look at is position isomerism. Position isomerism is where we have a functional group in more than one position in our molecule, from one isomer to the next. Let's have a look at propanol. So prop, 3 carbons, it's an ol alcohol. So I can have my OH group on the first carbon, or I can have it on the middle carbon. So these two molecules are isomers of each other. They've got the same molecular formula, a different arrangement of atoms. So this is propan 1 ol, and this would be propan 2 ol, because the OH group is on the second carbon in the chain. With position isomerism, the difference between these two molecules, it might be in terms of their physical properties. So there might be there will be a very slight difference in this case in boiling points, again due to the way that the molecules are able to pack and the strength of the intermolecular bonding as a result of that. But it will also have effect on their chemical properties. So for example, propan 1-ol is an example of a primary alcohol because the OH group is on the end of the chain. Here we have got a secondary alcohol because the OH group is in the middle of the chain, in very simplistic terms. Primary alcohols can be oxidized, as can secondary alcohols. If I oxidize a primary alcohol, I end up with an aldehyde, which has this functional group. Okay, I'm not going to bother drawing on the remainder of the hydrogens. If I oxidize a secondary alcohol, on the other hand, I get a ketone, where my carbonyl group is in the middle of the chain, as opposed to on the end of the chain. So, carbonyl group on the end of the chain, and I've made an aldehyde. Carbonyl group in the middle of the chain, and I've made a ketone. They're different molecules. They have really quite different chemical properties. Aldehydes can be further oxidized to form carboxylic acids. Ketones can't be further oxidized. So when we're talking about position isomerism, we're looking at where the functional group is in the molecule. It will have a small effect on physical properties, but it may have quite a considerable effect on chemical properties, particularly further down the line if we are doing a series of reactions. And finally, that brings us to functional group isomerism. So this is where we've got molecules with the same molecular formula, but the atoms are arranged differently such that we end up with different functional groups. And this is going to have a huge effect on both the physical and the chemical properties. So let me give you a classic example. I'm going to go back to this molecule here, butanol. So I can have, let's put my OH group in the middle. So 4 carbons, this would be butan 2-ol. And its functional group isomer is this molecule here. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this molecule here, well, let's say our first one is an example of an alcohol. And this molecule here is an example of an ether. This particular one is called ethoxyethane. Let's start off by thinking about their physical properties. You might be asked to predict their boiling points. Well, I can see straight away that butanol would have a higher boiling point than ethoxyethane. Why? Because it's got an OH group. It's capable of hydrogen bonding. Ethoxyethane, on the other hand, doesn't have an OH group. It's incapable of hydrogen bonding. We're just going to have permanent dipole intermolecular bonds, and of course both of them are capable of London forces or instantaneous induced intermolecular bonds. So, higher boiling point, simply because it's capable of stronger intermolecular bonds. Well, boiling point today. In terms of chemical reactions, well, we've already seen what alcohols are capable of. We can oxidize butan 2-ol to form a ketone. We can substitute the OH group for, say, a chloride or a bromide. Butan 2-ol, alcohols in general, are pretty reactive, really useful for making other molecules and chemical reactions. Ethers, on the other hand, well, they're not very reactive at all. In fact, they're almost inert. They're great for use as solvents, but other than that, we're hardly going to come across them at A level. So simply by changing the position of the oxygen atom between these two isomers, we're ending up with different functional groups and very different chemical properties. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A level. Together we can do this.